relational model of database management system. The contents that we are going to discuss in today's class would be the structure of an RDBMS, how the overlay of the schema, integrity constraints that can be assigned to the data, and the languages that could be used for querying relational data, which happen to be the relational algebra and tuple relational calculus. The textbooks are like this: the Database Management System by Raghuram Krishnan and Korth. For any further reference, you can go through them. Coming to the structure of an RDBMS. Generally, a relation happens to be, a database happens to be a collection of tables. Now, every table must be integrated or the data must be relational. Hence, we are going for an RDBMS management system. So, every row in a table is called as a tuple. That is the terminology which we will be using for defining a record in a relational model. So, the structure of it would be like this. Every attribute will be having a specific domain. You will be having multiple attributes for each and every record. So the domain of the attributes all put together happens to be a subset of the total set of attributes. If there happens to be n number of attributes, the domain of each, the Cartesian product of the domain of each of those n number of attributes form the relation. Now the tuple variable, the terminology, we get familiarized with the terminology and then get into the actual part of it. Tuple variable. In a general terminology, we call it as, we denote it as a T, wherein every T it belongs to the relation R. Each record will be specified in the following. Looking into the example, suppose our relation happens to be a student, the attributes of which are the student number, student name, and branch. So to denote each and every value in a single record, so T of S number is if the first roll number happens to be 510. It can also be denoted as T of 1. If you are going to the next record, then you should be having a subscript of 1 like that for every T values. Else, for the same one, T1 will be first value in the first cell, T2 will be value in the second cell, and T3 will be value in the third cell of the same record. Now coming to the database schema. This is very much similar to a relational schema only, but of course with a different notation. It's a programming language notation which is similar to the type definition which we have already learned in the structured programming in C. So every database instance is the data that is available at that particular point of time when you are querying. So same would be the definition for a relational instance also. It's a program language notation of the value of a variable at the point of your querying or referring to it. Now the schematic representation of the data. Let us take this particular example of a banking enterprise wherein the tables or the relations in this particular database schema happens to be the customer, branch, account, depositor, loan, and borrower. In this particular application, every customer who would like to be associated with a bank should have an account. So their name, if they open an account, their name will be registered in the customer table. And also, if it is an account, then the account number will also be linked with the depositor. Similarly, depending upon the type of activity the customer is performing, taking a loan, the particular information will be recorded in the loan and the borrower table. So customer is information of all the data of all the people who are using this particular application. Referring to this particular table, we don't get any data regarding whether that person happens to be a loan holder or an account holder. To refer to it, we should be linking it with the depositor or the borrower. In a branch table, it records the list of all the branches that are available across various cities and the assets that are available in the respective branches. So that's how it is aligned with the blocks of information. The title of the table is above the block. The key value which denotes every record, or rather which could identify every record in the table, is highlighted, and put in a box. Then you find the arrows directing towards the table's end, also pointing outward from the table. So this would say that the arrow head implies that it is the prime value to which the tail of the arrow is linked with. That's how the schematic diagram of various relations that exist between the tables in a particular database schema is represented. Coming to the constraints, you need here we have three categories of constraints. You call it as a super key, a candidate key, or a primary key. Now, to find out what is a super key, a single attribute or more than one attribute which can collectively differentiate every record in a relation is stated to be a super key. That means no two tuples agree upon the same value of the content in the respective columns which you have identified it as a super key. Now you can list any combination, n number of permutations and combinations of the attributes that are available in the relation, out of which it should be narrowed down to find out the list of candidate keys that could be available. So a candidate key is the definition wherein no proper subset of it is again a super key. That is it's a minimal super key, which one or two could be identified depending upon the size of the relation. And out of all those, one of it will be selected for primary. So here, now when you have a primary key in a particular relation, like I told you in the previous schema layout, wherein a customer name will be known if it is available in the depositor, that person happens to be account holder, or if it is in borrower, then the person is a loan holder. Similarly, so to link up those two, we need the information regarding differential integrity, a parent table which records the primary key and a child table which is going to record a foreign key. So this is referring to the existence of the data, the parent table, which we call it as a referential integrity.